But there's this really kind of famous data set that people use for two-way illustration. It was actually, the data was collected at Ohio State University, so it's just kind of in our backyard. So I thought it would be kind of neat to look at it. And I gave this illustration to my Math 6600 students this summer, and they seem to enjoy it, so hopefully you will too. What they did for the beer goggles example is they took a group of students in, and one thing that they looked at, obviously, was the gender effect. So they wanted to see if there was a difference across males and females. And the second thing they did is they varied the amount of alcohol. And I think they had no alcohol, 2 pints, and 4 pints. And what they did in the none, they actually gave them beer, but it just didn't have alcohol in it. So the people who were participating in the study were either given 2 or 4 pints of beer, and if they were given 2 pints of the alcohol, it was recorded as 2 pints. If they were given 4 pints of the alcohol, it was recorded as 4 pints. If they were given 2 pints or 4 pints of the non-alcohol beer, it was recorded as none. Well, the the measurement at the end of the night was the attractiveness of the mate that the person actually ended up leaving with. So what they essentially wanted to do, and I'll read this a little more in just a second, is if we think about step 1, looking at the null and alternative hypothesis, they first of all wanted to test if there was any difference in mate selection across males and females. All right, no comments. The second thing they wanted to do is see if there was any difference in means across no beer, or no alcohol at least, 2 pints and 4 pints. So the alternative here would be at least 1 pair of means. Differs. And guys, the final thing they wanted to do is they wanted to be able to tap into the marginal means and see if there were any difference in these things. In all these different comparisons of marginal means. So in this case, the null hypothesis would be that gender and alcohol have no interaction. Effect on mate selection. Okay, so I'll let you get that written down. May have to pause here. And the alternative hypothesis, I'm going to cheat a little bit here, the power of the eraser, is that gender and alcohol have an interaction effect on mate selection. So that looks kind of goofy when you're looking at it not in video form, but you can back up and see the null and alternative hypothesis. So guys, the steps we're going to do, first steps you'll always want to do in a two-way ANOVA is state the three pairs of H sub O, H sub A. The second thing I want to do always is explore the descriptive statistics. And what we'll want to do here is we want to look at some basic numerical summaries. And I want to look at some graphs. Guys, the third thing I'd want to do is test my assumptions for the model. You guys remember the assumptions for the model would be independence. Guys, again, independence is typically tested in the design of the study. Homogeneity of variance. I forget which one of you always butchered homogeneity of variance. I think, Christy, I think it was you. I can't remember. And, of course, normality. Okay, so the fourth thing we're going to do is we're going to conduct the two-way ANOVA. And what we'll do here really depends on what we get. If you think about it, we're going to have sum of squares and degrees of freedom and mean square and F and P values for our factor A, our factor B, and our interaction effect. Well, in this situation here, our factor A is gender, our factor B is the beer intake, and then of course this would be the beer intake across gender. And what we'll do here is we'll concentrate on these three p-values. Now, what I always do first of all is I have tunnel vision on this one, because in my opinion, and there's differing beliefs on this, but in my opinion, that if the interaction effect is statistically significant, I tend to minimize the effect of these two. So if the interaction effect is statistically significant, then I'm going to want to look at an interaction plot, and I'm going to want to look at at a Tukey multiple comparison. Now, if the interaction effect is greater than 0.05, what I would do then is I would rerun the model without the interaction, and I would focus just on the main effects, A and B. Now, in this situation, gender, we have two groups, obviously, male and female. So I would be looking at an independent samples T-test. And in beer content, I have three groups, none, 2 pints, and 4 pints. So for this, I would run an ANOVA for B. Now, I would only do this if my p-value, after eliminating, if I eliminate the interaction effect and just run a standard two-way ANOVA without the interaction, then I'm going to again focus on these p-values. For example, if my p-value was less than 0.05, I don't know why in the world my pen's not writing right there. But if my p-value is less than 0.05, then I would look at an independent samples T-test to see where the differences lie. If my p-value for this factor B was less than 0.05, then I would explore that difference in terms of an ANOVA. So I ultimately get these p-values by running a two-way ANOVA without the interaction, but my reaction to that is if the p-value is less than 0.05, I'm going to explore the differences for gender with an independent samples T-test, probably an unpooled. And if this is less than 0.05, I'm going to explore it with an ANOVA. So we'll see what happens. I really don't remember what happens in this example of beer goggles, but hey, we're going to find out, right? So the fifth thing I'm going to do is either number one, explore an interaction plot. And a Tukey, multiple comparisons. This is going to happen if our interaction is statistically significant. Or I want to examine the main effects independent of the interaction effect in our model. Okay. Now, as you would expect, I'm sorry. We want to tap into effect sizes, and you got to remember, guys, what our effect sizes here. We examined 3 of those. We examine it for factor A. We examine it for factor B, and of course, we examine the effect size for the interaction of A and B. We also examine power for each of these independently. So we can construct a power for this main effect, the second main effect, and independently of the first 2, we can calculate the power for the interaction effect. So, guys, let's see what happens. I really don't remember what happens, but I think it's kind of cool because I remember Ruth Hopkins and Jessica Drapesa did this for their midterm project, and it seemed like it was kind of fun. But let's see. Let's just see what happens. All right, gang. First thing, here's the problem. It's a psychologist at the Ohio State University. I don't know why that annoys me, but it does. Was interested in the effects of alcohol mate selection in nightclubs. The rationale was that after alcohol had been consumed, subjective perceptions of physical attractiveness would become more inaccurate. This is what we call, well, they say it's a well-known beer goggles effect. So looks like she picked 48 students. Hopefully these were randomly selected. 24 males and 24 females. Now you can see that she took 8 participants to a nightclub and gave them a placebo. 8 got 2 pints of strong lager, and 8 got 4 pints of strong lager. And of course, by doing this for each gender, she ended up with her 48 participants. At the end of the evening, she took a photograph. This would have been a fun study, but well, whatever. Took a photograph of the person that the participant ended up chatting with. Afterwards, she got a pool of independent raters to assess the attractiveness of the person in each photograph. Now, if it were me, we're going to run into something probably very soon called a covariant. And I would want to run a two-way ANOVA here. A covariant gives me a baseline that we begin with, and we see this in education data all the time. You can't just simply say that you gave a test, and if a student who scores a 99 or 100, well, they're the ones that learned the most. Hey, they may just come in knowing more. So, and we're going to explore this in great detail, but sometimes we include what's called a covariate. Well, I think it would be important here if I were going to try to publish this to come in with a covariate of the attractiveness rating of the participants in the study. Because I don't know about you, it's not that I hang out at bars a lot, and really, to be honest with you, I never really liked the bar scene. But when I had certain buddies that were just, they were just, most girls thought they were good-looking guys, and it seemed like they ended up leaving at the end of the night with the better-looking girls, so to speak. So I think I would want more here, but it's a fun illustration for a two-way ANOVA. So gang, the first thing that we need to do is we need to get the data in Excel and convert it to CSV. And just to save time, I've already done that. And I did it appropriately. My first variable is gender. My second variable is the amount of alcohol that the person was given. And I called the quantitative measure, I just called it looks, because that's the average of 100 scores on the attractiveness rating of that person. So apparently this guy right here was thought to be really hot by the independent observers. Well, this guy right here apparently wasn't thought to be so hot. So, take that for whatever it's worth. So, let's crunch the numbers. So, I'm going to save this. I think I've already saved it. So let's get this into R and go ahead and make some things happen. So, guys, first thing I need to do is, as we all know by now, and then I'm going to go get my data. I forget what I called it. Just goggles. Okay, makes sense. And I need to attach it. Yeah, I really don't care about looking at it. I like to have the names up there. That way I know that the way the variables have been, the way they've been written, whether because is alcohol capitalized or something, that makes a difference in R. All right. So, guys, as I told you, the very first thing I'd want to do is just explore some descriptive statistics. So I'd like to examine a measurement of center. I'm just going to choose the mean as you would expect. So I'm going to go T-apply, and I want to look at looks over gender, and I want to look at the mean. So the average attractiveness quality that females ended up talking to at the night were 60.21 and males were 56.45. So not a tremendous difference. Females look like they were a little pickier, but not a tremendous difference. Next thing I'd want to do is I'd want to look at looks over alcohol. And okay, we start to see a little bit of a difference here, don't we? The attractiveness quality of the people who drank had no alcohol was 63.75. It was actually a little higher for those who had 2 pints, but those who have 4 pints, looks like they weren't quite as picky after the 4 pints. Guys, I'd like to also look at the variation. So I would like to look at looks over gender, and I would like to look at the standard deviations. Actually, let's look at the variances. And wow, huge difference in the variances of mate selection. I don't know about that. I'm suspect of that. Let me type my data and make sure that there are no typos. Okay, well, this looks like that's just the way it goes. Okay, so I want to look at the standard deviation too on those. So let's look at looks over gender, and let's look at the standard deviation. So there's a lot more variation in the male attractiveness across gender. Okay, let's look at looks across alcohol, and quite a bit more variation over the 4 pints. So, all right, well, it is what it is. I'd like to look just at a histogram of my measurements for looks. Make sure we haven't got anything wacky going on there. We'll officially test that this looks like it came from a normal distribution, but that clearly to me looks like evidence of coming from a normal distribution. And I'd like to also do a box plot, and I'd like to look at a box plot of looks over gender. And you can see the variation difference in not only from the low score to the high score, but also the interquartile range. And I'd like to look at the box plot of looks over alcohol. And this will probably be kind of funny. I don't know. Let's see what happens. So 4 pints, the highest mate selection of 4 pints was equivalent to Q3 of 2 pints and no pints. And you can see that the first quartile was significantly below the lowest mate selection at 2 pints and no pints. So, you know, again, these are descriptive statistic measurements. These are only speaking for the 48 participants in our study. Guys, next thing I want to do, let's check the assumptions. And again, first assumption is going to be independence. And this assumption is typically checked in the design of our study. You know, this is the way our data is collected. It doesn't look like there's any threat to independence. For example, if the researcher just went out and started, just say they went to some bar where there was a lot of couples, and they just went up to couples and started asking them if they wanted to be in the study. Well, that would be a threat to independence, because there might be studies out there that show that better-looking males end up with better-looking females. So if you include both of them in the study, then there could be a threat to independence. Guys, the second thing that I want to test is homogeneity of variance. All right, so let's do that. So the first thing I'm going to do is run Levine's test. And to do that, I've got to install a package. And the package that I need, is car. And it's going to ask me to select a crayon. I like those folks at UCLA. And give it time to work. And the next thing I want to do is access the library for car. All right. So let's run it. So we have Levine test of looks across gender, and I want my center to be equal to the mean. And as you would expect from the box plot and examining the variance, we are violating the homogeneity of variance assumption across gender. Probably going to violate it here too. Well, just barely, but it's kind of like being barely pregnant. If it's below 0.05, you got statistical significance. You guys remember, and this is one of those things that'll probably pop up on your midterm. What are the null and alternative hypotheses for Levine's test of homogeneity of variance? Well, for gender, the null hypothesis would be that the variance for male is equal to variance for female. The alternative hypothesis would be that the variances are different. So we have more support for the alternative hypothesis in this case. For this Levine's test, the null hypothesis would be that the variance for no beer equals the variance for 2 pints equal the variance for 4 pints. And the alternative hypothesis would be that at least one pair of variances is statistically significant or different. Okay, so we got something going on here. We're violating the homogeneity of variance assumption, but again, research has shown that violation of the homogeneity of variance isn't a major threat to the stability of our p-value. So next thing I want to do is, this is going to be number 3. I want to test for normality, for looks overall, and looks across gender and alcohol. All right, gang, so what I'm going to do here is I'm going to run the Shapiro test for looks, just overall, okay? And, okay, I have to admit, I'm really surprised at that. Because the null hypothesis would here would be that it appears to come from a normal distribution. And we've violated that. Okay. Well, next thing I'd want to do is I'd want to run the by. I'd want to look at the Shapiro test for looks across gender and across alcohol. So I'm going to run looks for gender, and I want to run the Shapiro test. And it appears the reason that we got the statistical significance here may be because the looks for female don't appear to have come from a normal distribution. All right, let's explore this a little more. I'm actually finding this kind of interesting because this is not what I expected. So the Shapiro test, we aren't rejecting the null, so we're assuming normality. When we look at the Shapiro test across, or when we look, I'm sorry, at normality of looks across 2 pints, no pints, and 4 pints. So it appears like something's going on right here for gender. And I didn't see any major deviation across female in the scores here. In fact, that looks very symmetric to me. So guys, I got to admit, I don't know. I don't understand this. But I would trudge on and let's get busy on the analysis. So guys, the third thing I want to do is I want to run the conduct the analysis, and I want to include the interaction effect. So I'm going to call this fit 1 because I may end up getting fit 2, or so on. So I'm going to run AOV, and I want to run looks across gender by alcohol. If you just type fit 1, you get some good enough stuff. I mean, the thing I like there is it gives you degrees of freedom nicely. But I'm going to want to try to get the ANOVA table. So I'm going to do summary fit 1. And I get my p-values and F statistics and so on and so forth. Now, first thing I look at is gender across alcohol. I'm not going to throw the baby out the bathwater and forget this up here. But this tells me that the differences in mate selection are relying on some interaction between gender and alcohol. So 4 pints may not have affected the judgment of males like it did females, or vice versa. Or maybe it had been the 2 pints. There appears to be some interaction with gender. So I don't know. We've got to take a look at this stuff. So guys, we have a significant statistically significant interaction effect. So the next thing I'd want to do is I'd want to look at an interaction, an interaction plot, a marginal means plot, and those are really easy to get. Now, what I want to do here is I want to put in my my factor, and I'm going to show you both. I'm going to put gender in first, and then alcohol. This is not the way I would have done it, but it's going to be okay. And so what we look for is we look for a difference where we have non-parallel lines. Now, these lines aren't parallel, but there's not a lot of difference in the slopes of these two lines. It's a common belief that if we have lines that intersect, if they cross, that you have an interaction. Actually, I can show you. an example that it would take me a while to find it. That's not always the case, but day in, day out, you can look at the slopes of these lines and think about in terms of statistical significance. Those two slopes aren't that drastically different. So what it appears to me, this line right here appears to be the 4 pints. So there appears to be a statistically significant difference in mate selection. Notice the male is much lower than the female, but there doesn't appear to be that drastic difference in mate selection across 2 pints and 4 pints. Now I think we're going to get a better indication, and this is why I didn't do the one that I would have done first, because I want you to understand sometimes you got to explore this stuff. And I think this one may give us a better indication. If I look from 2 pints to 4 pints, notice that I have intersecting lines. Now my lines are given across males and females. So from 2 pints to 4 pints, there was a drastic difference in male compared to female. See guys, look this is actually cool. If we look at none, so when we look at across gender of no beer, notice that the mate selection for males was actually higher than for females. But that's not enough to create statistical significance. Over here, we have a difference in mate selection. Males are, for 2 pints, males are still apparently more selective than females. But man, I'll tell you what, the guys they lose their minds and go insane once they get 4 pints in them. There's a drastic difference. Looks like mean attractiveness rating about a 36 or 37 for males versus about a 57, 58 for females. So I'm going to expect that what's going on here happens with the big difference between males and females at 4 pints. Now, I would still like to go ahead and run a Tukey HSD. I like plots, but I also like numbers. So, guys, if we come in here, we're looking for the p's that adjusted p-values that are less than 0.05. So this tells me that there's a statistically significant difference between males who drank 4 pints and females who drank 2 pints. There's also a statistically significant difference between males who drank 4 pints and males who drank 2 pints. And a statistically significant difference between males who drank 4 pints and females who drank 4 pints. And we've got statistical significance down here between females who drank none and males who drank none with males who drank 4 pints. The guys, if you notice, in every p-value, what's the common theme? Well, there's male 4 pints. There's male 4 pints. This one, male with 4 pints. These two down here, male with 4 pints, male with 4 pints. All right, so seems like when males drink 4 pints of beer, they lose their mind and just decide to take anybody or talk to anyone. So, guys, we did have statistical significance back here for alcohol, right up here. So I would want to run an ANOVA. So I'm going to call this fit 2. And I want to run an ANOVA of looks over alcohol only. And, I'm going to bet that I get statistical significance for the obvious reason. So what I'd like to do now is I'd like to take a pairwise T-test. And notice I'm not coming up here. I'm not going to explore any more the main effect of gender, since it wasn't statistically significant. But the pairwise T-test, what I want to do here is I want my quantitative across my categorical, which is alcohol, and I want my p-adjust method to be equal to the Bonferroni. Yeah. And you can see what's going on here just for the alcohol. Taking out the gender effect, there's a statistically significant difference between 2 pints and 4 pints. And there's a statistically significance between 4 pints and no pints. But there's no statistical significance between 2 pints and no pints. So the common denominator here is the 4 pints, which is showing up even when we include the gender effect. Now, I want to have the summary of Fit 1 handy because I'm going to come in and do my effect size. So my effect for gender, hopefully you know that it's it's the square root of my degrees of freedom. And I'm going to put that in there just to make a point. Times the F statistic, which is 2.032, divided by the overall sample size, which is 48. Guys, my effect for alcohol is the square root of the degrees of freedom times the F statistic divided by the degrees of freedom. And the effect for the interaction is the square root of 2 times 11.911 divided by 48. Alright, so the effect for gender is 0.20. And I forget the threshold on this, but we can go look it up. So the effect for alcohol, I'm expecting pretty high here, yeah. Very, very high effect. And the effect for the interaction, I'm also expecting to be very high. Okay, so we'll keep that in mind. And the next thing I'd want to do is my power. So I'll tell you what I'm going to do. I'm going to write these effect sizes down, so I'll have these things. So the effect size for gender is going to be equal to 0.206. And for alcohol, because guys, what I'm getting ready to do, 0.914. And for the interaction is 0.704. What I'm going to do is go to G power, and I don't want to have to come back and forth. So let's go over and check the calculate our power. So guys, our family of tests here is clear. And we want to come to ANOVA with main effects and interactions. And what I want to do, I want to check for the interaction first. So my effect size for the interaction effect is 0.704. Well, shoot, guys, I'm doing the wrong thing. I want to conduct a post hoc achieved power. All right, let's. So my effect size 0.704. My total sample size was 48. My degrees of freedom for the numerator were A minus 1 times B minus 1, which is 2. And my number of groups would be, think about it, I have 2 gender, 3 on alcohol, so I have 6 total groups. So I'm going to say I'm going to probably have very significant power. And I do. I have 0.99. Some people may argue that's too much power. Let's calculate the power for, I'll tell you what, let me write this down because I'm going to show you how to write this stuff up. So we have a 0.99 power for the interaction. For the alcohol, we have 0.914. The error probability, total sample size is still 48. For alcohol, it's still going to be 2. The number of groups, we're going to have 3. So I'm looking at the main effects now, and I'm looking for alcohol. And well, again, we have extremely high power. a situation where, well, I don't know what's going on. I think I do, but I'd have to look at it more. Let's see, degrees of freedom 1. Here's 2. Probably be better off to go up here and do a independent samples T-test, but we calculate the effect size on Two Way Anova. And in this case, we only had 0.28 power. So it doesn't appear that we had enough power, but guys, what we're most interested in here is the power for the interaction effect. So guys, let's get out of here and go write up some stuff. So let me come down here and show you what we would do when we write it up. Now, you know, keep in mind that the quantitative measures part is primarily the 6610 and 6620. It's a non-theory approach, and at the end of the day, it's kind of getting you ready to conduct research, quantitative research for your senior project or for your capstone project. So we place a lot of emphasis on how we write up the results. So keep that in mind. Now, I kind of got sidetracked there because I was looking at something. When I ask you to write up problems, ultimately when you write up the big problem for your thesis, you're going to include descriptive statistics. But when you like your homework set right now, you have 5 homework problems. At least I think that's what it ended up being. You won't write up the descriptives. You'll just write up primarily the results. So, guys, this is the way that I would expect you to do that. So, it's the write up for alcohol, let's say. I would say something to the effect. I would say there was a significant main effect on the amount of alcohol consumed. At the nightclub, I guess we could say that. I don't know. On the attractiveness of the mate the subject selected. It's kind of wordy, but I think you get the drift. So I would want to come in and so I think we had 2,42. Guys, let me go back and check that. Yeah, 242. Okay, that's what I thought it was. All right, so 242, and the F statistic was 20.07, and our p-value was extremely low. And our effect size actually it's cone F, wasn't it? Was equal to, that's the reason I wrote this down, guys, 0.914. With achieved post hoc power of 0.99. All right, that's pretty. We can say the Bonferroni post hoc test revealed that the attractiveness of selected mate was statistically significant. Because I've written down some numbers here, and I can't figure out what I wrote down. So let's see, the selected mate, I've got it on my iPad. Okay, I see what's going on. Was significantly lower after 4 pints than both after 2 pints and no alcohol. So both p-values were less than 0.01. The attractiveness, let's see, it was greater than 0.05. Okay, so the attractiveness of mate selection after 2 pints and no alcohol were not statistically significant. All right, that's a little clumsy, but that's pretty much what we got in a nutshell. Gang, we would say for, let's see, well, what do we, let me check what my notes here. So we did not have statistical significance. Okay, so there was not, I guess we could say non-significant differences. Tell you what, let's go. There was a non-significant difference for the main effect of gender on the attractiveness of the mate selected. And I know we had degrees of freedom 1. Oh, shoot, guys, I can't read my notes. Looks like 2 something. So 2.03. P-value is equal to 0.161. My CONF was equal to 0.206. Was achieved post hoc power of 0.28. It's good to write this stuff down. All right, this one's going to be a little more involved. This one's going to be a lot more involved. So I would say something, there was a significant interaction effect between the amount of alcohol consumed and the gender of the subject. On the attractiveness of the partner selected. And guys, I know this is F242, and it looks like from my notes this is 11.91 with a p-value less than 0.01. Now with Cohen F equal to 0.914, which is a high power, and achieved post hoc power 0.99. Alright, so this indicates that male and female genders were affected differently by alcohol. More specifically, the attractiveness partners was similar in males. They had a mean of, jotted down here, 66.88. Standard deviation equal 10.33. And I've jotted down a male for 60.63. I'm trying to look at my notes and I didn't write as well as I wished I had at 12.52. So I'm referring back to the so that was the appropriateness was males and females after no alcohol. And the attractiveness of partners in males so it looks like the mean for this was 66.88. Standard deviation 12.52. And we saw females with 62.50. Standard deviation 6.55. So after no alcohol, so the attractiveness of partners, actually we should say males and females was also similar. After 2 pints, and the guys blow it. So all I'm doing here is just looking at the marginal means. All right, so however, the attractiveness of partner selected by males, and I have 35.63 with a standard deviation equal to 10.84. Again, just doing nothing fancy here, guys. Just it's a cumbersome mess because it's I've written all this stuff down on a sheet of paper and my writing wasn't very good. So the attractiveness of partners selected by males was significantly lower, and we saw this in the interaction plot. And if I were writing this up, you would definitely want to include the interaction plot that you're getting this information from in general, but I just ran the means and stuff, the marginal means. So lower than the partners selected by female, and females had higher standard. Imagine that. after 4 pints of alcohol. Now guys, I think this is, this took a long time, but I think this is pretty thorough. The only thing that I would really, as I look back on it, and I'm not going to go in and do this because I've illustrated this before, what I would like to do is I showed you back, I think in the Anova video, or maybe it was the Two Way Anova. I'd like to actually come in and present the effect sizes for each of these. So after this, after the no alcohol, I'd like to come in and actually give the effect sizes there. But I've shown you how to do that in a previous video. And hopefully you've learned by now that you know, I'm going to bombard your brain with R commands. And you don't want to get in a situation where you have to go back and watch videos. So what you need to do is, and I told you this early on, you need to get an R notebook and write down all this stuff as you go along. Because you know, you don't want to get in a situation where you got to go back and watch an entire video just to find one R command. So guys, this is a very thorough write-up for this problem. Take a screenshot or whatever and put it in your notes, and you'll use this again. So guys, that's all I got. Take care.